Okay, so hello everyone. Well, in this video, I wanted to make an introduction into how you can solve AC circuits using mesh analysis. Okay, so well, I have prepared the following exercise in which we have a voltage source right here. Now we have here a voltage source. And also we have another voltage source right here. We have a capacitor of 0.25 farads. We have an inductor of 2 henries, and we have a resistor of 4 ohms. Okay? So remember that the first step for solving AC circuits is to first convert all of the components into the frequency domain. So the first thing that we can convert into the frequency domain is the value of the voltage sources. So for example, if I convert this voltage source of 20 times the cosine of 2 times t volts, this into the phasor form will be 20 with an angle of 0 degrees volts. Okay? Remember that we are taking the amplitude and the phase angle. Here, we don't have a phase angle. That's why I am placing as a phasor a 0 degrees angle. And the magnitude of this phasor is 20 based on the amplitude of the sinusoidal. And also we can convert the 12 times the sine of 2 times t volts source into the phasor domain well, first we need to convert the sine wave into a cosine wave. And remember that we need to subtract minus 90 degrees to the argument. So this will be equal to 12 times the cosine of 2 times t minus 90 degrees. And this is equal, well, into the phasor domain will be equal to 12 with an angle of minus 90 degrees volts. Okay? And also we can convert the elements of the circuit like the resistor in the frequency domain. So we have 4 ohms, and this is 4 ohms in the frequency domain. We have the 2 Henry capacitor, sorry, inductor, and the impedance of the inductor is J times omega times L, and this is equal to J times omega, that in this case is 2 radians over second. Remember that omega is this value, okay? So omega is 2 radians over second, and L is the value of the inductor, that in this case is 2 henries. So this is equal to 4J ohms, and well, that's it. Now we need to convert the capacitor into the frequency domain, so it is 0.25 farads into the frequency domain is 1 over J times omega times C, and this is equal to 1 over J times omega, that is here 2 times the value of the capacitor, that is 0.25 farads, and this is equal to minus 2J ohms. Okay? Okay, so we have all of this. Now we can redraw the circuit into the frequency domain by using the impedance that we calculated and the phasors that we just calculated. So we can express this as follows. We have here the voltage source. Okay, we have here the resistor of 4 ohms. The value of this voltage source is in the phasor domain is 20 with an angle of 0 degrees volts. Here we have another connection. Here we have the capacitor, and the capacitor has an impedance of minus 2J ohms. And we also have the impedance of the inductor, that in this case is 4J ohms. And also we have this other voltage source. And the value of this voltage source is, well, is 12 with an angle of minus 90 degrees volts. Okay? Now, we want to apply mesh analysis, okay? That is the intention of all of this exercise. So remember that to apply a mesh analysis, what we can do is to first identify the loops or the meshes of the circuit. So for example, basically a mesh is a closed loop in the circuit. For example, the 20, well, this voltage source, no? This resistor and also this capacitor form a loop, okay? There is a closed loop in this part. Okay, so we can say that this is one of the meshes of our circuit, no? This is a closed loop, no? Or this is a mesh. Let's assume that the current in this mesh goes into this direction, okay? Goes from the negative to the positive terminal, and I will label this mesh as I1, okay? And also we have another mesh, no? That is this closed loop in which we have the capacitor, the inductor, and this other voltage source, okay? And I can also say that the current in this mesh goes in this direction, okay? That is I2. Okay, so we have all this information, and what else we can compute? Well, remember that in the original circuit, we wanted to compute the value of I sub 0, that is this current. So we can define this current in this region, okay? Now, what else we can do? Well, the idea of the mesh analysis, now that we have identified the loops of the circuit and to define the directions of the currents, the idea is that we need to apply to each of the meshes the Kirchhoff voltage law. Okay? So we want to apply this law into the circuit or in each loop of the circuit or in each mesh of the circuit. So for example, if I apply the Kirchhoff voltage law to mesh 1, remember that the Kirchhoff voltage law states that the addition of all the voltages in a loop should be equal to 0. That means that the addition of this voltage source plus the addition of the voltage of the resistor plus the addition of the voltage in the capacitor should be equal to 0. Okay? So if we apply this Kirchhoff voltage law into this loop, we will obtain the following equation. In this case, we need to be careful related to the direction of the current. Here you can see that I1 is flowing from the negative to the positive terminal. So I place a minus sign, and this is 20 with an angle of 0 degrees volts, plus the voltage of the resistor. Remember that the voltage is equal to the impedance or the resistance times the current, okay? So here the impedance is 4 ohms, and the current that is flowing through the 4 ohm resistor is I1, okay? Now, we need to compute the voltage of this inductor, okay? And we can say that the voltage in this inductor is equal to the current I0 times the impedance, okay? You can see that the I0 current is flowing through the capacitor, and in order to compute the voltage of the capacitor, we need to compute the value of this current times the impedance, okay? So this is equal to I sub 0 times the impedance of the capacitor, that is 2J ohms, okay? And well, according to the Kirchhoff voltage law, the sum of all of these values should be equal to 0. Okay? So that is a crucial point to consider. Now, we need to generate the same expression for mesh number 2. So for mesh number 2, okay, just wait a moment. Mesh number 2, we need to apply the the Kirchhoff voltage law to this second loop. Okay. So the first thing that I will express is the voltages that I can compute based on current I2. Okay, so based on the direction of this current, we can see that we have a voltage in this inductor that is equal to I2. Okay, remember that I2 is the voltage that is, sorry, is the current that is flowing through this inductor. That is 4 times J ohms. Okay, and you can see that this current I2 is flowing through the positive to the negative terminal. So in this case, and that is why it is very important that you see the direction of the current, since the current is entering through the positive terminal, I will place a plus sign, okay? So we have here 12 with an angle of minus 90 degrees volts, okay? But I am missing something. I am missing to consider the voltage in the capacitor, okay? But to compute this particular voltage, I will assume that there is a current right here that is flowing in this direction, okay? That is flowing also in the same direction in which the current I2 is flowing, okay? So let's say that this current, okay, is, let's label this as Ix, okay? So this current Ix, if we look closely to this diagram, we can say that Ix is equal to minus I sub 0. No, they are basically the same current, but they are pointing in different directions. So to denote that, I will place in this negative sign to I0 because basically Ix is the same value of I sub 0, but in a different directions. Okay? So we can say that the voltage in this inductor, okay, should be equal to, I will write this as the voltage of the capacitor is equal to Ix times the impedance, that is minus 2J ohms, okay? But we know that Ix, okay, that Ix is equal to minus I sub 0. And this is minus 2J ohms, okay? So that is very important because now I am analyzing based on the direction of this current, okay? So we can substitute this as the voltage of the capacitor for mesh number 2 is plus minus I sub 0 times minus 2J ohms, and this is equal to 0, okay? And, well, I think that's it, okay? And we have defined two equations. We have two equations with some incognitas. We have I1 and I sub 0, and here we have I2 and I sub 0. We have two equations with three incognitas, no? Because we have I1, I sub 0, and I2. But if you analyze in particular this node, you will notice that if we apply the Kirchhoff current law to this node, I will label this as node 1. In node 1, we can see that I1 is entering the node. And the ones that are leaving are I sub 0, no, I sub 0 plus I2. I2 is also leaving that node. So we have I2. So we can say that I sub 0 is equal to I1 minus I2. Okay? So now we have three equations with the three incognitas that we need. Okay? In fact, we can solve the circuit, no, by using these relationships. Okay? So there is another way in which we can compute these relationships more easily. Okay? instead of making all of these substitutions. So I will generate this mesh analysis um, by using a little different approach, no? So for example, I will rewrite the circuit, okay? Only to make this point a little bit clearer. And I will place here the 20 with an angle of 0 degrees voltage source. Here we have a 4 ohm resistor. Here we have the capacitor. And I have the impedance, that is 2 times J ohms. And here we have an inductor. And the inductor is of 4 J ohms. And here we have another voltage source. And the voltage source is of 12 with an angle of minus 90 degrees volts. Okay? And we have here the directions of the currents. Here we have I1. Here we have I2. And, well, what else? What else? Well, I will apply the same approach. Remember that we have two meshes in this circuit, okay? And we need to apply the Kirchhoff voltage law to each of the loops. Okay, we have one loop, another loop right here. Okay, we have the loop of I1 and the loop of I2. So again, if you look at the direction of I1, is flowing from the negative to the positive terminal. So we have minus 20 with an angle of 0 degrees volts plus, and remember, I will make the assumption that the drop in voltage in this element is positive. Okay, so I need to multiply 4 ohms times I1. I am making that assumption, okay? And the current that is flowing through this capacitor should be equal to the difference in currents between the two meshes. In other words, the current that is flowing through this element, we can say that is equal to the difference in currents between the two meshes. That is I1 minus I2. That is the current that is flowing through this element. And also I will assume that the voltage drop in this element is positive. And I multiply this current by the impedance, that is minus 2 J ohms. And this is equal to 0. Okay? And this is for mesh number 1. Now, let's do the same for mesh number 2. Okay. So for mesh number 2, we need to look at the flow of the current I2 and see and calculate the voltages based on this current. So for mesh number 2, you can see that I2 is flowing through the inductor that has an impedance of 4J ohms. So you multiply I2 times 4J ohms. And also you can see, based on the direction of the current, that I2 is flowing from the positive to the negative terminal. So I will place a plus sign to the voltage of this voltage source. That is 12 with an angle of minus 90 degrees volts. Okay? Plus the voltage of the inductor. And I will make the assumption that the voltage drop in this capacitor is also positive. Okay? That's why I'm placing a plus sign. But now I will compute the current that is flowing through this capacitor by using as a reference this loop as the difference in currents between I2 and I1. So here we have I2 minus I1. From the perspective of this mesh, I will assume that the current that flows through this inductor is equal to the difference in currents between mesh number 2 and mesh number 1. That's why I'm placing this relationship. And I am multiplying all of this by minus 2 J ohms. And this should be equal to 0. Okay? So you can solve these two equations in which you have two incognitas, I2 and I1. Okay? We have two equations with two incognitas. We can plug in these equations in the calculator. And you will notice that the value of current I1 is equal to 4.123 with an angle of 14.0362 degrees amperes, okay? And I2 is equal to 2.2360 with an angle of minus 25.5650 degrees amperes, okay? Now, what else we can do? Well, if you analyze very closely, you will also notice that at the beginning of the problem, we needed to compute the current I sub 0, okay? But this current I sub 0 is essentially, or we can compute the current I0 as follows. Here you can notice that if you analyze this node, that the current I1 is entering that node, okay? So based on the Kirchhoff current law, I1 is entering that node, and this current I1 is split between this part, this branch, and this other branch. So this current I1 should be equal to I sub 0 plus I2, okay? So we can say that I sub 0 is equal to I1 minus I2. So we can plug in these values into this expression, and we will notice that I sub 0 is equal to 2.8284 with an angle of 45 degrees, and these are amperes, okay? So this is like a brief example into how you can start analyzing AC circuits using mesh analysis, okay? The main point here is that you need to be very careful in how you are defining the directions of the currents and also in identifying correctly the closed loops in the circuit or the meshes of the circuit. So that's all for me. I hope you like this video. As a final step, I would like to express this current I0, I sub 0 in the time domain. So we can say that, just a moment, that I sub 0 in the time domain is equal to 2.8284 times the cosine. Remember, the frequency of the circuit is 2 radians over second times t plus 45 degrees, and these are amperes, okay? So, well, that's all from me. I hope you like it, and see you later.